Hello, everyone. I'm Dr. Junwei Liang. In this talk, I will present our solution for the AICT challenge, naturalist driving action recognition. Our work is titled Stargazer, a transformer-based driver action detection system for intelligent transportation. We propose an action detection system, namely Stargazer, which includes an improved version of the multi-scale vision transformer and an efficient framework. As shown in this graph, our system takes multi-view video stream and temporary localized actions. Our system achieves second place on the public leaderboard. Our framework can be adapted for other types of video stream with object detection and tracking modules. Here's the overview of this talk. I will present in details our framework for action detection, which includes action proposal module, action recognition module, and a post-processing module. I will then present our system experimental results. First, let's look at an overview of our Stargazer system. The graph shows that our system takes a single view video stream as inputs. It goes into the action proposal module, which extracts video clips with a constant number of cropped frames with temporal overlap. Then the action recognition module takes the proposal frames and classify the video clips into one of the distracted or normal driving actions. Finally, the post-processing module aggregates the overlapping classification scores, as well as multi-view results to produce the final action instance in the format of its start and end time. Given a video stream, here's the action proposal module in detail. We first extract action proposals where the action might appear. We utilize a 6-tuple to represent the spatial temporal queue proposal, as opposed to a queue proposal. The queue proposal is defined by the two-dimensional spatial coordinates and the start and end time, T0 and T1. The queue proposal with tracked objects may introduce arbitrary camera movement relative to the static background, which might impact performance of the recognition model. So you can refer to this paper below for a comparison between the two proposal designs. And in this work, since the driver occupies most of the video frames, we set the whole frame as the spatial crop. For temporal length of the proposal, we use 16:4 or 32:3, depending on the classification model. 16:4 means that we sample 16 frames at 4 frames right. The proposals are temporally overlapped. We use a sliding window approach to get final temporal resolution outputs. Here we present our core action recognition module. Given a proposal video clip, we utilize the multi-scale vision transformer V2 to classify the clip into one of the 18 classes in this dataset. Note that due to the code of MVIT V2, which is published at CVPR' 2022, the code is not released, so we did not implement the relative positional embedding as in the original paper. The key idea for the MVIT model, as opposed to the popular VIT vision transformer, is to decrease spatial resolution of the features and increase the channel dimensions in stages in order to achieve better speed accuracy trade-off. The key design is the multi-head pooling attention, which uses 3D convolution to decrease the spatial resolution. Here, MVIT V2 adds an residual connection, as the red arrow here, to the original design. Here we describe the training process. We first pre-train our model on Kinetics 700 dataset, which is a multi-class classification dataset with fixed length video clips. So there are about 650,000 10-second video clips with one of 700 class labels each. The annotation of AICT are variable length, which is different from the Kinetics 700 annotation. So as shown in the figure, given the training videos, an action instance of a certain class might cover different temporal lengths. You can see the different lengths of the different classes in this video. We cut the annotated variable length clip and then take them to perform random spatial and temporal cropping during training. So given the spatial crop, given the video clip of a certain class, we randomly we take a random spatial temporal crop from the video clip in each mini batch for training. We find that not using the clips with no annotation works better. In terms of post-processing, we use a simple but effective method by averaging all the scores onto frame level. So with a 64 frame proposal and 16 frame Windows strike, the frame level scores would be changing about every 0.5 seconds with a 30 FPS video. Action instances are produced based on continuous frames above a score threshold, as shown in the graph on the right. For the AICT challenge data, multi-view videos for the same act are provided. So for each action, for 5-minute video, you have 3 views. And then for each video, the action instance for each action class with the top average score is selected. Then we select the action instance with the most frames across multiple views. This is a simple strategy for us for the post-processing. Here we show the final results on the A2 validation set. We achieved 2nd place on the public leaderboard. This run is based on a 16:4 MVIT V2 model with a spatial crop of 448. The model is initialized from 224 model pre-trained on Kinetics 700. We trained 200 epoch on the A1 dataset with the multi-crop training I mentioned before. And we did not apply for the best model, we did not use any other data augmentation like mix-up or random augmentation. Here are some interesting ablation studies we conducted on one of the split on A1 dataset, which means we take 4 drivers for training and 1 driver for testing. We can see here are some of the conclusion. Mix-up does not help. Longer schedule helps. So 100 epochs has 37 top 5 error, but with 200 epoch, you can reduce that by a small margin. And obviously, larger spatial crop model helps significantly. So you can see here with a 448 crop versus the 224 crop model, the error reduced. We reduced the top 5 error by 12%. And longer clips helps. In this table, we can see helps a lot by a small margin, 35 versus 32. But we did not see this improvement on the A2 validation set on the leaderboard. And here we share an important future work that we think is promising in the field, which is efficient long-term video detection. The action detection model should be conditioned on a cached feature representation of past video stream. If you listen closely, you will see that our model currently our system has a lot of wasted computation, repeated computation, right? You have a sliding window approach. Ideally, the model should be able to cache all this feature computation, and then for the next time step, the model should be conditioned on the previously cached features so that we can expand the temporal horizon from seconds to minutes without exponentially increase our computation cost. Here are 2 papers that I think are very relevant and recent. Thank you all for listening, and our code and model are released on GitHub, and we also have provided the Kinetics 700 pre-trained model. Please give us a star, and for more details, please refer to our paper. Thank you.